Hi everyone, I am Gencer Sumbul. Today I will present one of our recent works, a relevant, hard and diverse triplet sampling method for multi-label remote sensing image retrieval. This work has been done with Mahdyar Ravanbakhsh and Begüm Demir under remote sensing image analysis group of TU Berlin and has been supported by ERC grant BIGART. Here is my outline. I will first explain the aim of the work, then go to the proposed method. After giving the experimental results, I will finalize the presentation with conclusion and feature ideas. As we already know that recent developments in satellite technology have led to fast-growing archives of remote sensing images. Accordingly, one of the most active topics in remote sensing is the content-based image retrieval from those archives. You can see its illustration in this slide. Image retrieval aims to find similar images to a given query image from an image archive. This is achieved by comparing image descriptors, which are obtained by feature learning step. Recent image retrieval methods utilize triplet-based deep metric learning to obtain image descriptors due to its proven success. In these methods, image triplets, including anchor, positive, and negative images, are fed into a convolutional neural network that provides image descriptors. Triplet loss operates on the descriptors of image triplets to learn a metric space where the distance between positive and anchor is minimized while that of negative is maximized. The accurate selection of image triplets is a difficult task, especially for multi-label remote sensing images. Most of the existing methods either use all the possible image triplets or apply random selection. Random selection may lead to inaccurate selection of triplets due to the missing some of the important ones. Using all triplets significantly increases the computational complexity of the training. More enhanced methods, mostly introduced in computer vision, assume that each image is annotated by a single label and are not suitable to use for multi-label images. Accordingly, in this work, we aim to develop a method to construct a small set of the most informative and representative image triplets that leads to an accurate image retrieval for multi-label images while reducing the computational complexity of the training. Based on this aim, we propose a novel triplet sampling method. Our method first selects a small set of anchors from each training mini-batch, which are diverse to each other in the feature space by an iterative algorithm. Second, for each selected anchor, it selects positive and negative images based on their relevancy, hardness, and diversity by a novel strategy. Here, you can see the illustration of the proposed method. There are two main steps. First step selects diverse anchors from a training mini-batch B based on the extracted features from a CNN backbone. Second step selects corresponding relevant hard and diverse positive negative images for each anchor XA. Then triplet loss is calculated based on the selected triplets. With that, CNN backbone is updated. I will explain each step of our method in the upcoming slides. The first step aims at finding a small set of most representative anchors. To this end, we introduce an iterative algorithm to evaluate the diversity of images in the feature space from a training mini-batch B and accordingly select a small set of anchors. This algorithm starts with an empty anchor set A. Then the proposed diverse anchor selection strategy randomly selects the first anchor from B, which is put into A. After the first anchor, this iterative algorithm selects a new anchor which has the highest distance in the feature space from already selected anchors. The algorithm is stopped when the desired number of anchors are selected in total. The total number of anchors, H, is a method parameter. Since the selected anchors are as distant as possible to each other due to iterative algorithm, the diversity among them in the feature space is maximized. This leads to the selection of a representative set of anchors that forms the basis for the second step. The second step aims at selecting positive and negative images for each anchor that are relevant and hard, in other words, informative, and diverse to each other in the feature space means representative. To this end, we introduce a novel relevant, hard, and diverse positive-negative image selection strategy. The relevance of an image to an anchor is calculated based on its multi-label similarity with the considered anchor. The hardness of an image is defined based on its distance to an anchor, and the diversity of a positive image is measured based on the distance among other positive images, and it is the same also for negative images. Accordingly, this strategy initially calculates the positive and negative informativeness scores that consider relevancy and hardness. A positive image is associated with the high relevancy if its class label similarity to the anchor is high. A negative image is associated with the high relevancy if the class label similarity is small. A positive image is defined as hard if its distance to the anchor in the feature space is high, while a negative image is regarded as hard if its distance to the anchor is small. Beta is weighting parameter to give more importance to either relevancy or hardness of the image. This strategy starts with empty positive and negative sets for each anchor. Then first positive image P1, which has the highest positive informativeness scores with the anchor, is selected. Similarly, the first negative image N1 is selected based on the negative informativeness score. After selecting the first positive negative images, other images are iteratively selected, similar to the first step, to select also most representative positive negative images in addition to informativeness. It is stopped when the desired number of positive negative images are chosen, which is K as a method parameter. Gamma defines the influence of the diversity term. This strategy ensures that the selected positive negative images for each anchor are informative, in other words, hard and relevant, and representative means diverse among each other in the feature space. After selecting the final set of triplets from the mini batch B, the triplet loss is calculated and backpropagated through the backbone. Let me give you the experimental results. We conducted experiments on VS Merced Land Use Archive. This archive includes 2,100 aerial images. Each image has the size of 256 by 256 with a spatial resolution of 30 centimeters. We also use the multi-labels of each image from 17 distinct classes. Here you can see an example of images and their multi-labels. For the backbone of the method, we used ResNet 50 CNN architecture. You can also see the selected parameters in the slide. The number of anchors and positive negative images are 10, which is 10% of the mini batch size. To analyze the effectiveness of each step, we compared diverse anchor selection with batch anchor selection that uses all the possible anchors and random anchor selection that randomly selects the anchors. We also compare our relevant hard and diverse positive negative image selection strategy with batch anchor positive negative image selection and random positive negative image selection. We compare the proposed triplet sampling method with two methods. First method randomly selects both anchor and positive negative images, and second method uses all the possible triplets. To the experiments, we created the train test and validation sets. The validation set is used to select query images, while images were retrieved from the test set. In the first table, you can see the comparison of anchor selection strategies when the proposed positive negative image selection was used for all of them. This table shows that selecting diverse anchors significantly increases the image retrieval performance compared to random anchor selection or using each image in the mini-match as anchor. In the second table, you can see the comparison of positive negative image selection strategies when our anchor selection strategy was used for all of them. Similar to the first one, in this table, our strategy achieves the highest metric scores compared to others that shows the effectiveness of the proposed positive negative selection strategy. In this table, you can see the metric scores for different triplet selection methods. When compared to the first one, which randomly selects triplets, our method provides significantly better results under the same number of triplets. This shows that our method selects image triplets more accurately than the random selection. When compared to the second method, which uses all the possible triplets, our method improves the image retrieval performance under a significantly smaller number of image triplets. This shows that our method accurately selects image triplets while reducing the computational complexity of training due to a smaller number of applied operations during triplet loss calculation. In this work, we introduce a novel triplet sampling method for multi-label remote sensing image retrieval problems. We can say that our method is promising because it selects a compact subset of informative and representative triplets that leads to accurate and efficient learning of deep models in the context of triplet-based deep metric learning for multi-label remote sensing image retrieval. It is worth noting that for our method, all the selected triplets are equally considered in the triplet loss calculation. As a feature work, we plan to develop a weighting strategy to take into account of relevancy and hardness scores of images during loss calculation. Thank you for listening to me. I would be happy to hear your questions.